So today is class 15. We have a quiz today on classes 12, 13, and 14. We'll do it at the end of class. And project 3 is due on Friday. You have homework due today because it's Wednesday. The homework that we did last week is from class 12 and 13. Class 14 is not due. If you have it done, you can hand it in. I'll give you credit for it now. Okay, so today we're going to start with a quick review of composition of functions. So this is something you've seen in a couple of previous classes, pre-calc and college algebra. So composing two functions, when you plug one function into another. So if f of x is e to the x and g of x is 3x plus 1, what is f of g of x? Good, e to the 3x plus 1. So you take the g function and you plug it into the f function for all the x's. All right, so part of the language that I'm going to use today when we're talking about composition of functions is inside function and outside function. So looking at f of g of x, what would you call the inside function? G of x, right, because it's going into f, right? So g of x we call, I'm not even going to write g, I'm going to say it's the 3x plus 1. When you look at the composition, e to the 3x plus 1, we call 3x plus 1 inside. And what would we call the outside function? E to the x. E to the x we refer to as the outside function. So e to the 3x plus 1 is a composition of two functions, e to the x and 3x plus 1. And we call one of them the inside function and one of them the outside function. All right, what would g of f of x be? Yep, 3 e to the x plus 1. Good. So in this case, what's your inside function? E to the x. E to the x is the inside function. And what's my outside function? 3x plus 1. Okay, so we're going to learn how to find derivatives of compositions of functions today. And we use something called the chain rule, which I'm not going to write down until after we do a bunch of these. So the key idea when you're taking the derivative of a composition is to apply the normal derivative rule, then multiply by the derivative of the inside function. Okay, so apply the normal derivative rule, then by the derivative of the stuff. Right, so think of this first one as y equals e to some stuff. What is the derivative of y equals e to some stuff? E to some stuff, right? The derivative of e to the x is e to the x. So the derivative of e to some stuff is e to the stuff. But then you're not quite done. When you're taking the derivative of composition, you apply the normal rule, but then you also have to multiply by the derivative of the stuff. 3, right? The derivative of 3x plus 1 is 3. So in this case, y prime would be 3e to the 3x plus 1. So for b, I have some stuff squared. How do you take the derivative of, say, x squared? 2x, right? You use the power rule. I'm going to use the power rule on this. Bring the 2 down. 2 times 3x plus 4 to the first, right? So I just applied the power rule to the stuff. But then you also have to multiply by the derivative of the stuff. What's the derivative of 3x plus 4? 3. So if you only have to do one step or two steps to simplify your derivative, go ahead and do it. Multiply 2 times 3, and you get 6 times 3x plus 4. Or even a second step and distribute 18x plus 24. If one or two steps can significantly simplify the expression, go ahead and do them. But if it would take like 3 pages to simplify your derivative, you can just leave it. So that's going to be our sort of our standard rule for simplification. Okay, so you guys try C. Take the derivative of this stuff to the 23rd. Okay, so I have some stuff to the 23rd power. I'm just going to apply the power rule to the stuff. So y prime is going to be 23 times x squared minus x plus 1 to the 22. So apply the normal rule, just do the power rule, but then you're not quite done. You still have to multiply by the derivative of the stuff. And what's the derivative of x squared minus x plus 1? 2x minus 1. This is one of those cases where I would not make you simplify it, because raising a trinomial to the 22nd would take you pages and pages and pages of work. All right, let's take a look at D. 4 to some stuff. Y equals 4 to some stuff. So y prime, well, what's the derivative of 4 to the x? 4 to the x ln 4. So my derivative of this guy is going to be 4 to the x squared plus 5x times the ln of 4. Right? 4 to the stuff times the ln of 4. But then you still have to multiply by the derivative of the stuff, the derivative of the inside function, which is going to be 2x plus 5. That make sense? All right, I'm going to do the next one on a separate page. Need a little more room, yeah. 6x minus 3 to the 10th and 3x plus 5 to the 14th. Oh, I knew I wouldn't bring. Thank you. Okay, so y prime. This is a product, right, of two functions. 6x minus 3 to the 10th times 3x plus 5 to the 14th, multiplying those two functions together. So I have to use the product rule, which we learned last class. So this is a good chance for us to review it before your quiz, too. Yep. So the product rule says first times the derivative of the second plus the second times the derivative of the first. So my first function is 6x minus 3 to the 10th. I don't have to do anything. I just copy it down, the first function, times the derivative of the second function. And because that derivative is a little bit complicated, I'm going to save it. I'm just going to write d dx of the second function. So this says first plus the derivative of the second. Sorry, times. First times the derivative of the second, plus the second, 3x plus 5 to the 14th, times the derivative of the first. And the first is 6x minus 3 to the 10th. So I've just written down the product rule. I didn't take the derivatives because those two derivatives in there are going to involve a little bit more work than usual. So just to keep my mind, keep things straight, I wrote down the whole product rule, and then I'll take the two derivatives. Yeah. Yes. Yeah, if you want to, you can use, you could just write the derivative down. Okay, so 6x minus 3 to the 10th times the derivative of 3x plus 5 to the 14th. Good. So we apply the normal power rule, bring the 14 down, put it in front of the 3x plus 5, raise it to the 13th now. But then we're not quite done. You still have to multiply by the derivative of the stuff, the derivative of the inside function, and the derivative of 3x plus 5 is 3. Okay, then we have 3x plus 5 to the 14th times the derivative of 6x minus 3 to the 10th some stuff to the 10th power. The way I take this derivative is I apply the power rule. So I bring the 10 down, copy the 6x minus 3, and then decrease the exponent by 1. So power rule applied. But because the inside function, it wasn't just a plain old x, it's a 6x minus 3, I have to multiply by the derivative of the inside function, which is 6. And then I guess we could simplify this a little bit. And I would get 42 times 6x minus 3 is a 10th. $60. All I did was multiply the constants together in that step. Because then it wouldn't be exact. Nope. All right, I want you guys to do f. Take the derivative of that square root of the quotient. Okay, so I saw lots of people rewrite this square root as a 2 to the 1/2. So we have 5x over 2x minus 1 to the 1/2. And then you have some stuff to the 1/2. Right? So if I want to take the derivative, I'm going to apply the power rule. So I have 1/2 times the stuff to the negative 1/2. So I just apply the power rule to the stuff. It's a very common mistake to take the derivative of the stuff and put it in here. Right? But you leave that alone. You apply the power rule to the stuff, then you take the derivative of the stuff and multiply by it. So now I want to do times d dx, a derivative of the inside function, 5x over 2x minus 1. And how do I take that derivative? Quotient rule. Yep. All right, so I'm going to have y prime is 1/2 times 5x over 2x minus 1 to the negative 1/2 times. So now I'm going to take the derivative of this quotient using the quotient rule. So the quotient rule is denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So I've got to start with denominator, 2x minus 1, times the derivative of the numerator, what's that? 5, minus the numerator, times the derivative of the denominator, which is 2, all over the denominator, 2x minus 1 squared. And so this is one of those cases where just a little bit of algebra will significantly simplify this, so you should do that. If you can make some significant impact towards simplification in a few steps, you should do it. Y prime is going to be 1/2 times 5x over 2x minus 1 to the negative 1/2. And then this ends up being negative 5 in the numerator over 2x minus 1 squared. So in the last one, we did the chain rule within the product rule. And in this one, we're doing the quotient rule within the chain rule. What? No, sorry. Okay, so here is the chain rule written formally. I haven't written it down yet. We've just been applying it using the the basic idea of apply the regular derivative rule, then multiply by the derivative of the stuff. So here's the chain rule written out formally. I've got 3 versions. Stuff is a technical term, yeah. So version 1, if you want to take the derivative of a composition, f of g of x, you do f prime evaluated at g times g prime. That is, if you want to use the stuff instead of g, take f prime of the stuff times the derivative of the stuff. In Leibnitz notation, if you want to take dy dx, if y is a function of z and z is a function of x, so we have a composition, y of z of x, right? And you want to take dy dx, you do dy dz times dz dx. And this is why we call it the chain rule, because you end up, this is just a composition of 2 functions, but if you had more, this looks like a chain. dy dz times dz dx times dx dt times blah, 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 blah. So this ends up looking like a chain of derivatives. And then the English version, which is the version we've been using so far, says to take the derivative of a composition, you take the derivative of the outside function, evaluate it at the inside function, then multiply by the derivative of the inside function. All right, so at this point in the semester, we don't have a good justification for why the chain rule works. So we're just going to have to just use it on faith for now. So here are 4 new derivative rules. We're going to prove them later in the semester. You're not responsible for knowing these yet, but just having them written there is going to allow us to do some more interesting chain rule practice. So let's say I want to take the derivative of the cosine of x squared. So I have some stuff squared, right? So first thing I'm going to do is apply the power rule, and I'm going to get 2 cosine x to the first, right? But then you're not quite done. We've applied the power rule, but then you have to multiply by negative sine x, the derivative of the inside function. The derivative of cosine x they gave us up here is negative sine x. So really small simplification here. And we have the derivative. All right, so for j and k, when I'm trying to find j prime and k prime, I'm going to do it using Leibnitz notation. When you're taking derivatives, you can do whatever method makes most sense to you. So far, we've just been using like sort of the English version. The Leibniz notation version can be really handy if you're just like stuck. You don't know what to do first. So first thing it does is you have to decompose your function into y equals something and z equals something. So in this case, I'm going to let y equal the ln of z, and that means that z would have to be what? X cubed, right? So I've decomposed ln of x cubed into y equals ln z and z equals x cubed. Outside function ln z, inside function x cubed. So I just separated it, those two, into an outer and an inner function. And then I'm going to write down the Leibniz notation for the chain rule. dy dx is dy dz times dz dx. All right, so dy dz, take a look at the y equals ln z function. What is dy dz? According to the rule that I put up above the questions. 1 over z, yeah. The derivative of ln x is 1 over x, so the derivative of ln z should be 1 over z. Times dz dx, what's the derivative of z here? 3x squared. Now all you have to do is substitute. The answer should only have x's in it because the original function only has x's in it. So all you have to do is substitute in place of z, put in the x cubed, what z equals. So this is going to be 1 over x cubed times 3x squared, which is 3 over x. Okay, so for k of x, let's decompose this into a y and a z. So I'm going to have y equals and z equals. So y is going to be your outer function. What's the outer function here for k of x? Arctan. So y is going to be arctan of z, and z then would have to be the inner function, which is e to the x. Good. So then I want to take dy dx, and the Leibnitz version of the chain rule says that dy dx is equal to dy dz times dz dx. Okay, dy dz. Look at the y function, arctan z. I want to take its derivative. I gave you the derivative rule, the last one on the right up here. 1 over 1 plus z squared. Yep. The derivative of arctan x is 1 over 1 plus x squared. So the derivative of arctan z would be 1 over 1 plus z squared. Then times dz dx. So I have to look at my z function, z equals e to the x. What's its derivative? E to the x. Now all I have to do is make the substitution, replace z with what it equals, e to the x. So I end up with e to the x over 1 plus e to the x squared, which is e to the 2x. So you can use whatever method makes sense to you. Just think of inner and outer functions, or apply the rule to the stuff, then times stuff prime, or the Leibnitz notation. Whichever one just sits the best with you, you can use that one. So I'm going to have you take 10 minutes or so to get a good jump on this group work, taking some derivatives. And don't worry, the chain rule is confusing at first, and we're going to spend a whole nother class talking about the chain rule. So this is not your only time you'll see it in class.